and you're told that the total current in this tube through this cross-sectional area is I naught. Uniformly distributed, right? So let me ask you this question, right? So there's current all over this tube. It's a very long, straight tube. What is the magnetic field generated by this current in this solid wire? Maybe I'll call it a wire instead of a tube. Let's say right here, at a distance r from the axis. How do I find the magnetic field there? What should I do?
Should use Ampere's equation.
Right? Okay, so we use Ampere's law. So we imagine an Amperian loop. This is a chapter 28 problem. And the current is constant. And then we write down this. So you multiply the magnetic field by the length around the loop, right? Because the magnetic field vector is parallel to the L vector, so the dot product will give you just the magnitude of the magnetic field times the magnitude of that. The magnetic field will be constant over that radius, so you put it outside, so it's B times the sum of the dl, so this will be just 2 pi r, right? And this is mu naught, and I enclosed is the total current through this. Which is going to be some fraction of I naught. So how do I find I enclosed? Knowing that this current I naught throughout the entire cross-sectional area of radius A is uniformly distributed.
Something equal to each other with their areas.
So I set up a proportion, so I do what? So for example, I enclosed is to what?
2 pi r.
Area of a circle. What's the area of a circle?
Pi r
So pi r squared. So in other words, I enclosed is to the area through which it's through, right? Going through. As the total current I naught is to the area over which that's distributed, which is, and they use that for I enclosed. So it'll be I naught over pi a squared times pi r squared, and then this will cancel that, right? So that's what goes over here. So be I naught r squared over a squared, right? And then solving for the magnetic field in the next line, right? This r cancels one of those r's. So the magnetic field at a distance r inside this wire is mu naught I naught over 2 pi a squared times r, right? Yes? So that's the magnetic field right there. The next question is this. You have this tube, right? If the current, since the current is to the right, what is the direction of the magnetic field over here at the top? What is the direction of the magnetic field?
Outward.
Out of the board, right? So B is out. And what is the direction of the magnetic field over here? Into, right? B is into. So if I now look at, and this is a wire, right, with cross-sectional area pi a squared, the radius is a, right? If I look at the plane of the board, on the plane of the board, and I ask you, suppose I consider a plane, a chunk of the plane of the board like this, and I call this length W, that's the width, and obviously this length over here will be the radius of the wire, then what is the total magnetic flux through this rectangle of width W and let's say height A? And the magnetic field all over the place is into all over the place. But notice that the magnetic field depends on the distance away from the axis. The further away you go from the axis, the greater, the stronger the magnetic field becomes. So how do I figure out the total magnetic flux through this plane? So it's like you have this tube like this, there's a tube like that, and I take a sheet and I go like this. But extending from the axis to the edge of the tube. So how do you find the magnetic flux through that? Then you can say, well, the magnetic field is changing with distance. So over this line over here, okay, of distance r from the axis and thickness dr, suppose I give it a thickness dr, since this, if I think of this thickness dr as being infinitesimal, that is very, very, very tiny, then I can assume that the magnetic field over this strip is the same, because dr is very small. So what is the area of this strip? WDR. And the magnetic field that's going through that strip is that we calculated over there. So what is the magnetic flux through that strip? That would be the magnetic field there multiplied by the area of that. So that magnetic flux will be the magnetic field at that distance r, which is mu naught I naught r over 2 pi a squared multiplied by the area of that strip, which is W dr. So that's the magnetic flux through the green strip. So what will be the magnetic flux through all of this? Well, since the magnetic flux has a dependence on radius, then what I need to do is I need to consider another strip and add it to this, and add it to the magnetic flux through the other strip, and add it to the magnetic flux through the other strip, and add it to the magnetic flux through the other strip, and that's called integrating, right? So you integrate both sides of this equation. So what are constants? Mu naught is a constant. The current is said to be a constant. The width of this, that is a constant. The 2, the pi, the a squared is a constant. And then you have r dr, right? And so this is the total magnetic flux. And here we're integrating with respect to r, so we integrate from what value of r to what value of r. So that I fill this rectangle with strips. When I consider my first rectangle, what's the value of r over there? 0. And when I consider my last strip over here, what's the value of r over there? So I integrate from 0 to a. And so the result becomes mu naught I naught W over 2 pi a squared. And what is the integral of r dr? Evaluated from 0 to a. Did I lose something in here or no? I have an r over here, and somehow it looks weird, but let me check. No, I think it's good. So this will become mu naught I naught. You know, you're gonna get an a squared, which is gonna cancel that a squared, right? And then a 2 and a 2 will give me a 4. Pi. And that's what I have. Yes?
Yeah, yeah.
That's what that is. That's Any other question? Okay, you look like you're ready for battle.